You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Quantum computing has emerged as one of the most exciting and challenging frontiers in technology, holding the promise of revolutionizing fields that depend on massive computational power, including artificial intelligence. Unlike classical computers that rely on binary bits, quantum computers harness the principles of quantum mechanics to perform calculations in fundamentally new ways. Their potential lies not only in speed but in solving types of problems that classical machines may never tackle efficiently, such as simulating molecules or optimizing complex systems. For AI, quantum computing offers the possibility of accelerating learning, expanding the range of solvable problems, and reshaping how algorithms are designed. At the same time, the field remains experimental, with significant scientific, engineering, and ethical challenges still to be addressed. This episode explores how quantum computing works, how it intersects with AI, and why its future represents both immense opportunity and profound responsibility for science, industry, and society. Quantum computing can be defined as computation based on quantum bits, or qubits, which differ fundamentally from the binary bits of classical computers. A classical bit can exist only in one of two states, 0 or 1. A qubit, by contrast, leverages quantum properties to represent both 0 and 1 simultaneously under certain conditions. This duality allows quantum computers to process information in ways classical machines cannot, enabling them to explore multiple possibilities at once. While the physical realization of qubits varies, from trapped ions to superconducting circuits, the principle remains the same: exploiting quantum states to perform computation. This approach opens doors to solving problems involving enormous search spaces, such as factoring large numbers or modeling complex molecules. Quantum computing is not just faster computation. It represents a new paradigm that challenges the very foundations of how we think about information, algorithms, and problem-solving in the digital age. The contrast between classical and quantum computing lies in how they represent and manipulate information. Classical computers operate through binary logic, flipping transistors on and off to create deterministic sequences of operations. Quantum computers, by contrast, operate through quantum states that are probabilistic rather than deterministic. Where classical systems evaluate one path at a time, quantum systems can evaluate many in parallel through quantum superposition. This does not mean they are universally faster. Quantum speedups apply only to specific kinds of problems, but it does mean they approach computation with entirely different logic. For example, simulating a protein's folding might take astronomical time on a classical supercomputer, but a quantum machine could, in principle, model it more efficiently by directly representing quantum interactions. The difference is less about raw speed and more about categories of problems. Quantum systems expand what is computationally feasible, creating opportunities to tackle challenges classical machines cannot handle effectively. Entanglement is another cornerstone of quantum computing, describing the way qubits can become linked so that the state of one instantly correlates with the state of another, even across distance. Entangled qubits allow quantum systems to process information in deeply interconnected ways that classical bits cannot replicate. This property enables stronger correlations in computation, enhancing efficiency in solving certain problems. For instance, entanglement helps error correction methods by distributing information across multiple qubits, making systems more resilient. Philosophically, entanglement challenges traditional notions of separateness, as changes in one qubit are reflected in its entangled partners. Practically, it creates computational pathways unavailable to classical architectures. Like superposition, entanglement is fragile, requiring advanced engineering to maintain. Still, it remains one of the most fascinating features of quantum systems, offering both a window into the mysteries of physics and a practical mechanism for unlocking computational abilities beyond anything classical machines can achieve. Quantum gates and circuits form the operational foundation of quantum computing. Just as classical computers manipulate bits with logic gates like AND or OR, quantum computers manipulate qubits with gates that rotate their quantum states. These gates, such as the Hadamard or CNOT, exploit superposition and entanglement to perform complex transformations. When arranged into circuits, they guide qubits through sequences of interactions that encode algorithms. Unlike classical circuits, quantum circuits must account for probabilistic outcomes, designing processes where desired results emerge with high probability. Building reliable gates is an immense engineering challenge, as quantum states are extremely sensitive to noise and interference. Yet, the conceptual elegance of quantum circuits mirrors classical computation, showing that despite their exotic physics, quantum machines remain programmable systems. Understanding gates and circuits helps demystify quantum computing. It is not magical, but a structured method of controlling fragile states to perform calculations beyond classical reach. Quantum algorithms showcase how this new computational paradigm can be applied. Famous examples include Grover's algorithm, which accelerates unstructured search tasks, and Shor's algorithm, which can factor large numbers exponentially faster than classical methods. These breakthroughs highlight why quantum computing has drawn attention not just from scientists, but also from industries like cryptography and finance. While only a handful of algorithms currently demonstrate clear quantum advantages, research continues to explore optimization, simulation, and machine learning tasks that may benefit from quantum approaches. Quantum algorithms are not simply classical algorithms running faster. They require rethinking problems in terms of quantum mechanics. They represent the creative intersection of physics, mathematics, and computer science, embodying the possibility of entirely new ways of reasoning about data. For AI, these algorithms hint at ways to accelerate training, improve optimization, or expand the complexity of models, suggesting that quantum systems may become catalysts for breakthroughs in intelligence research. Quantum computing holds special relevance for AI because many AI tasks involve optimization and high-dimensional search problems. Training deep learning networks, for example, requires adjusting millions of parameters to minimize error functions. Classical systems handle this through iterative computation, but quantum systems could, in theory, explore solutions more efficiently by representing many possibilities simultaneously. Optimization in logistics, scheduling, and resource allocation core to both AI and real-world applications could also benefit. By reducing computational bottlenecks, quantum computing may make advanced AI systems more scalable and adaptable. However, much of this potential remains theoretical, as practical implementations are still in development. The key point is that AI and quantum computing share overlapping challenges. Both seek to navigate complex, multidimensional spaces. Their intersection is therefore not accidental but inevitable, as advances in one field may provide critical leverage for breakthroughs in the other, shaping the next generation of intelligent systems. Quantum machine learning represents the hybridization of classical and quantum methods to tackle problems neither could solve alone. In these models, quantum processors handle specific subtasks, such as managing high-dimensional feature spaces, while classical computers manage broader processes. For instance, quantum systems might accelerate kernel methods in machine learning, or reduce the dimensionality of data more efficiently. The goal is not to replace classical AI, but to augment it, leveraging quantum strengths where they matter most. Early experiments show promise but remain largely proof of concept, as current hardware lacks the stability and scale for robust deployment. Nonetheless, the field is rapidly expanding, with researchers exploring algorithms that explicitly take advantage of quantum states for learning. Quantum machine learning embodies the spirit of hybrid intelligence, combining complementary strengths to unlock new capabilities. It also highlights that the path to practical quantum AI is evolutionary, building incrementally rather than leaping instantly into transformation. Quantum neural networks attempt to bring the structure of deep learning into quantum architectures. By designing networks where qubits act as nodes and quantum gates as connections, researchers hope to replicate, and perhaps surpass, the pattern recognition power of classical neural networks. These models could, in theory, learn and generalize across tasks, while benefiting from quantum properties like superposition and entanglement. For example, a quantum neural network might recognize patterns in molecular data more efficiently than any classical counterpart. However, challenges abound. Defining activation functions, managing noise, and interpreting outputs in probabilistic terms remain unresolved. Still, the pursuit reflects the ambition to merge two of the most transformative fields in computing. Quantum neural networks are more than a technical experiment. They symbolize a vision of intelligence built not on silicon transistors, but on the strange and powerful principles of quantum mechanics, pushing the boundaries of how machines might one day learn and reason. Variational quantum algorithms represent a practical bridge between current quantum hardware and ambitious applications. Because today's quantum systems are noisy and limited in scale, researchers use hybrid approaches where classical computers optimize parameters while quantum processors evaluate them. This iterative process leverages the strengths of both systems, allowing quantum devices to contribute meaningfully even before they reach full maturity. Variational methods are especially promising for approximate solutions to problems in chemistry, physics, and optimization, where exact answers are infeasible. For AI, they may help train models or explore parameter spaces more efficiently. Variational algorithms reflect a pragmatic philosophy. Rather than waiting for perfect hardware, researchers are building methods that make use of what exists now, accelerating progress while preparing for future scalability. They demonstrate that the quantum revolution will not arrive in a single leap, but through incremental hybrid innovations that gradually transform computational practice. Quantum speedups in search problems exemplify how quantum computing could outperform classical systems. Grover's algorithm, for instance, reduces the time needed to find an item in an unsorted database from linear to square root complexity, offering significant improvements as datasets grow. Applied to AI, this could accelerate training, optimization, or data retrieval in ways that reshape what is computationally feasible. While exponential speedups are rare, even polynomial improvements matter in practice, especially for problems with astronomical complexity. The excitement around quantum speedups lies not in every task becoming instantly faster, but in specific, high-value problems being solved more efficiently. For AI, where many challenges involve searching vast solution spaces, even modest speedups could unlock transformative capabilities. Search efficiency highlights the synergy between quantum mechanics and machine intelligence, showing how physical principles may directly expand the boundaries of computational possibility. Hardware challenges remain the most significant barrier to realizing quantum computing's potential. Qubits are notoriously fragile, prone to errors from environmental noise and quantum decoherence, which collapses superpositions prematurely. Building stable systems requires extreme conditions, such as near absolute zero temperatures and complex error correction protocols. Scaling qubit numbers while maintaining coherence is a daunting engineering task, with progress measured in small, incremental steps. These challenges explain why quantum computing, despite decades of research, remains largely experimental. For AI, this means most quantum applications are still theoretical, with few practical demonstrations at scale. Nonetheless, progress continues, fueled by both public and private investment. The hardware struggle underscores that quantum computing is not just about clever algorithms, but about mastering the delicate physics of qubits. Until these challenges are resolved, quantum computing will remain a tantalizing promise rather than a mainstream tool for accelerating AI. The debate over quantum supremacy captures the drama of progress in this field. Quantum supremacy refers to the milestone where a quantum computer performs a task no classical computer can complete in reasonable time. In 2019, Google claimed this achievement by demonstrating a quantum system solving a specific artificial problem in minutes that would take classical supercomputers thousands of years. Critics argued the task lacked practical relevance and that classical machines could approximate it more efficiently than claimed. Still, the announcement marked a symbolic moment, showing that quantum systems could surpass classical ones in at least some domains. For AI, the debate matters because it frames expectations. When will quantum systems provide advantages in meaningful tasks like optimization or learning? Supremacy milestones highlight progress while also exposing hype. They remind us that while breakthroughs are real, practical impact depends on translating demonstrations into usable, scalable solutions. Despite progress, current limitations make quantum AI largely experimental. Today's quantum computers are small, noisy, and prone to errors, limiting their practical use in machine learning or optimization. Many demonstrations remain proof of concept rather than scalable solutions. For AI practitioners, this means quantum methods are exciting but not yet reliable tools. Classical systems continue to dominate, supported by decades of refinement and vast infrastructure. Quantum AI remains a research field, promising but not yet proven. This gap between potential and reality is both a challenge and an opportunity. Researchers must temper expectations while continuing to explore new architectures, algorithms, and hybrid approaches. The lesson is one of patience. Transformative technologies often evolve slowly before sudden breakthroughs occur. For now, quantum AI is less about immediate utility and more about preparing the foundations for a future where its capabilities may be realized. Ethical and security implications of quantum computing are profound, especially as they intersect with AI. A primary concern is cryptography. Many current encryption methods rely on the difficulty of factoring large numbers, a task quantum algorithms like Shor's could solve efficiently. This threatens the foundations of digital security, from banking to government communication. At the same time, nations that achieve quantum breakthroughs could gain enormous strategic advantage, reshaping global power dynamics. Ethical questions also arise about equitable access. Will quantum capabilities concentrate in wealthy nations and corporations, widening technological divides? As quantum computing amplifies AI, risks of surveillance, misuse, or unintended consequences also grow. These issues remind us that technological revolutions are never purely technical. They carry social, political, and moral dimensions. Preparing for a quantum future requires not only scientific progress, but also foresight, governance, and global collaboration to ensure benefits are shared responsibly. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Applications of quantum computing in optimization problems illustrate one of the most practical and immediate areas of overlap between quantum mechanics and artificial intelligence. Many industries, from logistics to manufacturing, face challenges that involve finding the best arrangement among countless possibilities. Classical computers must often rely on approximations, as the sheer number of variables makes exhaustive search impossible. Quantum systems, by leveraging superposition and entanglement, can evaluate many potential solutions simultaneously, narrowing the field much faster. For example, a shipping company might use quantum optimization to design routes that minimize fuel use while meeting delivery deadlines, or an energy grid might optimize resource distribution across fluctuating demand. These problems are not just technical puzzles. They carry economic and environmental implications. By making optimization more efficient, quantum computing could reduce waste, cut emissions, and improve global supply chains. This application highlights how even incremental improvements in computational power can translate into transformative benefits in the real world. Drug discovery represents another domain where quantum computing could accelerate breakthroughs, particularly when paired with AI. The process of identifying promising molecules for new medicines often requires simulating quantum interactions at the atomic level, tasks that classical computers struggle to approximate accurately. Quantum systems designed to model quantum phenomena directly could evaluate molecular structures and reactions far more efficiently. For example, I might propose candidate compounds from vast chemical libraries, while quantum simulations refine predictions of how those compounds will interact biologically. This collaboration could shorten the timeline for developing treatments, reducing years of trial and error into months of targeted analysis. Beyond speed, quantum drug discovery offers precision, uncovering compounds that classical simulations might overlook. In a world where new diseases emerge and global health challenges grow, the ability to design medicines faster and more effectively has profound implications. It demonstrates how quantum AI could transform not just computation but human well-being. Financial modeling is another field where quantum AI shows potential. Markets are complex, with countless interacting variables, from stock prices to global events. Classical systems often simplify these dynamics, but quantum computing offers the possibility of analyzing them in richer detail. By representing multiple possible market states simultaneously, quantum systems could evaluate risk portfolios, optimize investment strategies, or detect patterns hidden in noisy data. For example, an investment firm might use quantum simulations to model how global interest rate changes ripple across sectors. Paired with AI, which identifies trends in historical data, quantum computing could provide insights with greater depth and accuracy. However, these applications raise ethical questions, such as whether quantum financial tools will widen inequalities by giving disproportionate advantage to institutions with access. Still, the potential is enormous. Quantum-enhanced financial modeling could stabilize markets by improving predictions, or destabilize them if misused, underscoring the dual-edged nature of this powerful technology. Climate modeling presents one of the most globally significant applications of quantum computing. Simulating Earth's climate involves countless variables: atmospheric chemistry, ocean currents, land use, and human activity interacting in ways classical computers struggle to capture at fine resolution. Quantum systems could represent these dynamics more accurately, enabling researchers to forecast extreme weather, study tipping points, or test mitigation strategies with unprecedented detail. For instance, AI might process satellite and sensor data to define parameters, while quantum simulations explore the cascading effects of carbon emissions on ecosystems. Such precision could inform international policies, guiding investments in renewable energy or adaptation infrastructure. Climate modeling with quantum AI highlights the intersection of science and ethics. The tools may exist to foresee risks, but societies must act on them. By expanding our predictive power, quantum computing offers hope for better stewardship of the planet, provided humanity uses the insights responsibly and equitably. Quantum-inspired algorithms provide another fascinating avenue, applying principles of quantum theory to classical systems. Even without quantum hardware, researchers adapt concepts like superposition and entanglement into mathematical strategies that improve performance on classical computers. For example, optimization problems can benefit from heuristics modeled after quantum annealing, which explores solutions by simulating quantum states. These algorithms have already been applied to logistics, finance, and machine learning with measurable improvements. Quantum-inspired methods illustrate a broader truth. The influence of quantum research extends beyond machines themselves into how we conceptualize computation. They also serve as a stepping stone, preparing industries to adopt full quantum systems when hardware matures. By delivering practical benefits today, quantum-inspired algorithms ensure that progress toward quantum AI is not all or nothing, but gradual, spreading insights and efficiencies even before true quantum computers achieve mainstream deployment. Industry investment in quantum AI is accelerating rapidly, with major technology firms, startups, and research labs competing to secure leadership. Companies like IBM, Google, and Microsoft have launched quantum cloud services, allowing researchers and businesses to experiment with algorithms on real quantum hardware. Startups focus on specialized applications, from drug design to supply chain optimization. This surge of investment reflects both technological promise and competitive pressure. Whoever masters quantum AI first could unlock enormous economic and strategic advantages. Yet the hype also risks disappointment, as timelines remain uncertain. For AI researchers, industry funding provides access to tools and collaborations that would be impossible otherwise, fueling innovation across both fields. At the same time, concentration of resources raises concerns about monopolization, where benefits accrue to a handful of corporations rather than society broadly. Industry investment showcases both optimism and caution. emphasizing the need to pair innovation with responsibility and accessibility. Government initiatives in quantum AI reflect recognition of its strategic importance. National programs in the United States, China, and the European Union dedicate billions to quantum research, often framing it as critical for security, economic growth, and technological sovereignty. Governments fund basic science, workforce development, and partnerships with industry, while also considering regulatory frameworks for responsible deployment. For example, national security agencies invest in quantum-resistant cryptography to prepare for risks of broken encryption. International collaboration occurs, but rivalry dominates as nations view quantum AI as a domain of geopolitical competition. Government leadership ensures that progress is not left solely to market forces, but it also raises ethical questions about militarization and inequality. The role of governments in quantum AI illustrates how emerging technologies blur lines between science, industry, and statecraft, making public investment a decisive factor in shaping both the pace and direction of innovation. Collaboration between AI and quantum fields reflects the natural synergy between disciplines. AI aids quantum research by helping control hardware, calibrate qubits, and interpret experimental data. Conversely, quantum computing promises to expand AI's capabilities by accelerating training and optimization. This feedback loop drives innovation. Machine learning refines quantum devices while quantum systems open new horizons for AI. Research labs increasingly bring together physicists, computer scientists, and AI experts to bridge gaps and foster hybrid solutions. For instance, AI models are used to stabilize fragile quantum systems in real time, reducing error rates. Collaboration across these fields exemplifies the interconnectedness of modern science, where advances in one domain unlock progress in another. It also highlights the importance of interdisciplinary education and partnerships, as the challenges of quantum AI require expertise that spans physics, algorithms, and ethics. Together, AI and quantum fields illustrate the power of convergence in shaping future intelligence. Standards for quantum computing are beginning to emerge, providing frameworks for interoperability and ethical practice. As multiple companies and nations pursue different hardware approaches, such as superconducting qubits, trapped ions, or photonic systems, standards help ensure that algorithms and software can transfer across platforms. International bodies and industry consortia are developing guidelines on performance benchmarks, error reporting, and programming languages. Ethical standards are also under discussion, particularly concerning cybersecurity and equitable access. Without shared frameworks, progress risks fragmentation, where incompatible systems slow collaboration and concentrate benefits unevenly. Standards also provide trust for businesses and governments, reassuring them that investments in quantum AI will remain usable as technology evolves. In this way, developing robust standards is as important as advancing hardware, ensuring that breakthroughs translate into scalable, responsible, and widely accessible applications, rather than isolated, proprietary silos. Workforce development is essential for preparing scientists, engineers, and policymakers to advance and govern quantum AI. The field requires a rare combination of skills, blending quantum physics with computer science, machine learning, and ethics. Universities are beginning to offer interdisciplinary programs, while governments and companies sponsor fellowships and training initiatives. Yet the talent gap remains significant, threatening to slow progress or concentrate expertise in a few elite institutions. Beyond technical training, workforce development must emphasize ethical and societal awareness, preparing practitioners to navigate issues such as privacy, equity, and international competition. For students and professionals, entering this field means embracing lifelong learning as the technology evolves rapidly. Workforce development illustrates that preparing for a quantum future is not only about building machines, but also about cultivating people who can guide, govern, and apply them responsibly across industries and societies. Barriers to adoption of quantum AI remain formidable, even as excitement grows. The cost of building and maintaining quantum hardware is immense, requiring specialized facilities and expertise. Infrastructure needs, such as cryogenic cooling and error correction, make deployment challenging outside elite labs. Expertise itself is scarce, with too few professionals trained in both quantum theory and AI. Beyond technical hurdles, political and economic barriers exist, as nations and corporations vie for control of resources and knowledge. These limitations explain why most current applications remain experimental rather than practical. Overcoming barriers will require sustained investment, global cooperation, and innovation in both hardware and training. While adoption may be slow, the stakes are high. Those who surmount these obstacles may unlock capabilities that reshape industries, security, and science. The barriers highlight that the journey to quantum AI is not simply technological but also infrastructural, social, and political. Case studies in quantum AI illustrate how research is beginning to explore practical intersections. For example, experiments have tested quantum-enhanced machine learning for image classification, using small quantum circuits to process data in ways that mimic classical neural networks. In finance, early prototypes apply quantum-inspired optimization to portfolio management, while in chemistry, hybrid quantum classical models simulate molecular behavior. These case studies remain preliminary, but provide proof of concept that quantum methods can contribute to AI and vice versa. They also highlight the importance of hybrid approaches. Most successful demonstrations involve blending quantum systems with classical computation, rather than expecting quantum devices to operate alone. Case studies remind us that progress is incremental, with milestones building momentum toward broader applications. They also provide early evidence that quantum AI is more than theory, offering glimpses of how collaboration between the fields may transform research and industry in the years ahead. The future of quantum AI promises breakthroughs that could transform computation, science, and society. As hardware matures, applications may expand from experimental to mainstream, accelerating drug discovery, climate modeling, logistics, and beyond. AI systems could train faster and tackle problems previously intractable, reshaping industries and expanding scientific knowledge. Yet the trajectory remains uncertain, with breakthroughs contingent on overcoming hardware challenges and governance questions. Optimists envision quantum AI as a catalyst for progress, driving solutions to global challenges. Skeptics caution that hype may outpace reality, leading to disillusionment. Both perspectives emphasize that the future of quantum AI is not inevitable, but shaped by choices in research, policy, and ethics. What is clear is that the combination of AI and quantum computing represents one of the most ambitious experiments in human history, blending physics, intelligence, and imagination to expand the frontiers of possibility. Long-term risks of quantum AI cannot be overlooked, particularly regarding cybersecurity, equity, and ethics. Quantum algorithms capable of breaking current encryption threaten the foundations of digital security, from banking systems to personal privacy. Without preparation, this could destabilize economies and undermine trust. Equity concerns also loom, as nations or corporations that achieve quantum breakthroughs first may consolidate disproportionate power, widening global divides. Ethical challenges include misuse in surveillance, warfare, or manipulation, where quantum AI's power could amplify harms. These risks highlight that technological revolutions are not neutral. They reflect the values and structures guiding them. Addressing risks requires proactive policies, international cooperation, and transparent standards. Long-term risks remind us that progress must be balanced with precaution, ensuring that the pursuit of quantum AI enriches humanity collectively rather than destabilizing it through concentrated, unregulated power. Preparing for a quantum future requires deliberate strategies across education, policy, and governance. Education must cultivate interdisciplinary expertise, producing professionals who understand both quantum mechanics and AI. Policies must encourage responsible development, such as supporting quantum-safe cryptography and ensuring equitable access to technology. Governance must balance innovation with regulation, preventing misuse while enabling progress. International collaboration will be essential, as quantum breakthroughs affect global systems of security, economy, and science. Preparing also means engaging the public, fostering awareness of both opportunities and risks. The goal is to ensure that quantum AI becomes a shared benefit rather than a divisive weapon. Preparation is not a single step but an ongoing process, requiring foresight and adaptability. By investing in people, institutions, and ethical frameworks, societies can approach the quantum future with confidence, shaping it not as a threat but as an opportunity for collective advancement. Quantum computing and AI together represent a frontier where physics and intelligence research converge, offering immense potential and equally significant challenges. Quantum principles like superposition and entanglement enable new computational paradigms, while AI provides tools to guide and amplify their application. Applications span optimization, drug discovery, finance, and climate modeling, showing that quantum AI could transform both science and society. Yet barriers remain: fragile hardware, high costs, limited expertise, and profound ethical risks. The lesson is that quantum AI is not a guaranteed revolution, but a possibility shaped by human choices. Its trajectory depends on whether societies pair innovation with foresight, ensuring equitable access, secure systems, and responsible governance. For learners, the takeaway is clear. Quantum AI is both a scientific marvel and a moral challenge, demanding not only technical brilliance, but also wisdom in guiding its power. It embodies humanity's quest to push boundaries while safeguarding the values that make progress meaningful. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.